Welcome to your favorite channel and a new video, this time on classification in machine learning. Once machines start learning, then what do? What do they output? They do typically four things. One, they take decisions. Two, they make predictions. Three, they map similarity. And four, they find patterns. So, taking decisions, making predictions, mapping similarity, and finding patterns. These are the four things that a machine does. Which of this is classification? Let us take a single industry and try to find out what are the implications of these four machine learning outputs. You can take retail, you can take telecom, you can take pharma, you can take healthcare. I have chosen banking industry. In banking, what's the meaning of decision when it is taken? What is a prediction? What do you mean by mapping similarity? And what is it finding the pattern? Let us take case number one of trying to make a decision. You would often find that simple letter that comes to you, sir, your loan has got approved. In rare cases, I haven't got it, but then people do get it. Sir, your loan is not approved. So based on a set of parameters, which we would later call as features, bank comes to a simple binary dichotomous conclusion, a one-point decision, either to give a loan or not to give a loan. That is decision. Take a very different scenario which is not related to decision at all. Tons and tons of customers come into a banking system every year, and not all of them are retained by the bank at the end of some time period. The typical time period could be 12 months or 1 year. Now, as a bank, I need to know how many of them am I retaining, or what is my YOY retention, or in other words, how many of them are leaving the system. What is a YOY churn? So churn plus retention is equal to 1. I would ideally like 100% retention. Nahi hota hai. Doesn't happen. So let us say I predict that I want 80% retention. So how do I get this 80%? That again is based on a lot of data, a lot of parameters, a lot of features which will drive some sort of output which will help me through the machine to predict that 80% of my customers would remain with me at the end of the year. That game is called prediction. Now take a third game, very dissimilar to what I explained so far. Banks today are trying to categorize their customers. Any industry which is classically in marketing called segmentation, you would want to create multiple categories of your customers. In the context of banking, that would be for providing differential service levels. You have the so-called right up there customers whom we call as high net worth individuals, and they get extraordinarily personalized service. Then you have not necessarily high net worth but good net worth individuals. For him, you have the relationship manager inside the bank. Then the normal customer who has got the teller counter. And then the fourth level, bank doesn't talk about them, but they really do not want to service those sort of customers at all. Now, let us come out of banking and try to look at what we are trying to talk. I need to create small groups of customers with an identical behavior, with a similarity in behavior. How do I do that? That is my output number 3. And the last one, I talked about it in detail in a previous video. It talks about the if-then mechanism, trying to find a pattern. If something is happening, can I find out any a priori thing which has led that to happen? Take an example of a check bounce. If my checks, the customer's checks are regularly bouncing, then can I go back and find out whether there is a credit card default pattern, whether there is any excessive credit card payment pattern, and whether that is because of a lower salary. So a low salary and thereby a high credit card pattern and thereby a EMI default, this can be predicted as a pattern. So these are some of the things that a machine can do in the context of banking alone. which of this is classification? You have guessed it right. Classification is taking decisions. Just to complete the picture, making prediction is regression, finding similarity or mapping similarity is clustering or cluster analysis, and finding patterns is association rule. 1 and 2, classification and regression, come under what we call as supervised learning, and 3 and 4, clustering and association rule, come under unsupervised learning. From now on, for this video, we'll only be talking about classification. What do you mean by classification? After doing a lot of analysis, I need to come to a clear decision of yes or no, true or false, give or not give, high or low, etc. So I need a decision boundary, and if my total data set is a two-dimensional data set, my decision boundary is a line. Anything that happens on one side of the line is one decision, and data points which lie on the other side of the line is the other decision. If my data set is a three-dimensional data set, which means I have three features over which my target is moving, then my decision moves from a line to a plane. It becomes a plane, and anything that happens above the plane versus below the plane bifurcates my decision. Extending this logic, technically, if I have n decision variables or features, I get an n-1 hyperplane. Let us not get into those complications right now. Let us keep it sweet and simple. Today we'll be talking by and large about binary dichotomous decisions. Before we look at classification, let us try to understand how do machines learn? Tricky question? Well, it's actually very simple. Let us try to compare the traditional programming way, which we have been seeing for maybe about 50-60 years, and the current machine learning way. So in a traditional programming way, what is it that I input to the computer and what is it that I expect from the computer? One, I input the data. The data anyway has to be given, but computer does not understand what to do with any data. So what do? I feed a program, I feed a software, I feed an algorithm along with the data, and then the computer understands for this particular data, using this particular algorithm, I'll get a particular type of output. A matrix multiplication could be an output. Okay, that is what we have been doing since the time of Adam and Eve of computers. But today, the game has changed. Now what do I feed? I anyway feed the input data. The input data has anyway got to be fed to the computer. Computer does not know about it. Then I feed the output data. So I iteratively feed the output data back to the computer. Now what does the computer see? Input, output, input, output. It tries to find out what could be the relationship between the input and this output. And after some point of time, it spews out an algorithm. The computer tells you what is the process, what is the rule, what is the mechanism that connects this particular input and the output, and that the machine has learned. That is why it is called machine learning. And it is this algorithm that decides in the case of classification, or that predicts in the case of regression. When we are talking about classification and about decision making, we straight away run into the biggest villain in the system: decision errors. So the game now gets into error reduction, and error reduction is a story of two trade-offs, completely different trade-offs. One trade-off is a century old. We'll briefly touch upon that, but we'll primarily concentrate on the second trade-off. The first trade-off that I mentioned to you, the century-old trade-off, is called the Neyman-Pearson trade-off. Didn't get it? Hey, that is a good old type 1, type 2 error, or the confusion matrix error. Related to your good old hypothesis testing, It talks about the power of your prediction in terms of statistical modeling. It talks about what is my desired confidence level when I'm trying to predict something. Am I happy with 90%? Many a time 90% is good, or should I take it to 95% confidence level, or in some of those supercritical cases, do I require a 99% confidence level? That will drive my alpha versus p-value, the things which we regularly do in type 1 versus type 2 trade-off. Is it gold? Of course it is gold standard, but unfortunately it is old gold. We now come to the second error reduction trade-off, the new age machine learning trade-off called bias versus variance. A complicated word for that is a bias variance decomposition trade-off, whatever that means. Now what is this? This trade-off is related to core data modeling. Do you want accuracy? Do you want your data to be accurately reflecting the scenario that you're trying to build? Obviously, yes. Do you want repeatability or consistency? Obviously, again, yes. But then, as it happens many a time in life, both of them cannot be simultaneously achieved to perfection. So the trade-off, the bias variance trade-off, is actually a trade-off between accuracy at one end and consistency or repeatability of the result at the other end. It talks about how well your model which you're building, the classification model which you're building, fits with the data that you're inputting. It's a reflection of the model data fit. Gold standard, again gold standard, but this is a new gold standard in error reduction. Before we move into the intricacies of the bias variance trade-off, I thought it would be prudent to spend a minute on the word trade-off. Your business world today, or business world any day, has always been a game of trade-offs. Examples: short-term versus long-term, profit versus environment, some say marketing versus ethics, innovation versus adaptation. I have given you two examples on the screen: cost versus quality. Take Hyundai, and if you keep on moving along the cost vector, you reach the Eon. Keep on moving along the quality vector without compromising on cost, you reach the Verna. So either cost or quality has to be compromised to create the product line in an automobile industry. The last example here would be equity financing versus debt financing, the core of capital restructuring and capital financing. Your weighted average cost of capital is a cost of how much equity and associated opportunity cost can you afford, and how much debt and how much leveraging can you afford. Is your business risk permitting you to take additional financial risk? Well, we close the trade-off game and move straight to what we are talking: classification and bias variance. Back to bias variance, and as I mentioned to you, both of them cannot be simultaneously reduced. So where is the middle line? Let us try to understand what's the meaning of a very high bias. You simply take one feature and try to predict the target. That game is called a linear game. That is, take the case of a heart risk. I want to predict whether heart risk is high or low, and I obviously know, we all know, that cholesterol is a key indicator for heart. So higher the cholesterol number, higher the risk for the heart. So I plot just one feature, cholesterol, versus the target heart risk, and I get a straight line. Obviously the actual scatter plot will lie all around this line. It doesn't fit perfectly into any line. Take the other extreme. I think of all sort of predictors which can drive a heart attack. Your sugar levels can drive heart attack, blood pressure, cholesterol, age, heredity, body mass index. I'm not a doctor. So let us try to find out all of them and map all those features, and suddenly you get a line that goes something like this. It tries to cover all your data points into fitting the training data. That game is called overfitting. I didn't mention the previous game is called underfitting. So one extreme you have an underfitted data with a linear model, and at the other extreme you have an overfitted data with a high-end polynomial model. Now, how do you do the trade-off? Here, my question is, do I want a very high accuracy or do I want a very high consistency? Let us first look at the training model. We need to get the training model anyway right. So, in case number 1, the training error is definitely going to be high because your points are going to lie all around this straight line. So the training error, which is what we call as the bias, that is why for the straight line, the bias is anyway going to be inherently high. Now what happens in the other case, since you're sort of overfitting the model, the bias automatically comes down. The accuracy of the model tremendously improves and the intrinsic training model does not have a bias. Now come to variance. Textbooks, blogs and literature talk about when the bias is high, the variance is low. I would tend to disagree with that. I would simply tell you that the variance also is high, but the variance in the high bias case would be relatively lower than the variance in the second case or the overfitting case. Let us talk about the variance in the overfitting case, which is more understandable. When we are doing an overfitting for a particular training model and then we try to move to a test model, obviously the cross-validation error between the training and the test is going to exist because it is highly overfitted, and that is going to give you a lot of variation in your outputs, and that variation is high variance. In the other extreme is when you're having a straight line, your bias is anyway going to be high. That doesn't mean your variance is going to be low. Variance also is high, but variance will be relatively lower compared to the overfitted scenario. Now, when I play cricket, I do not play cricket to perfect myself in the nets. I play cricket in the field. So I anyway have to go for my test modeling. And let us try to find out, after I reduce my bias using a good overfitting, how can I then reduce variance? That is where the video would move ahead. How to choose the middle road? The answer is random forest. Random forest modeling. Is that a unique middle road option? Not at all. There are plenty of middle road options. Some of them are non-parametric models like your support vector machines, neural networks, ensemble modeling, etc. But from an understanding point of view, not necessarily from an implementation point of view, from an understanding point of view in terms of model building, one of the easiest models to understand for Bias-Variance Trade-off is random forest. Random forest, step number 1, or should I call it intention number 1. I hate inaccuracy. So your feature target relationship, the way your target gets defined by your set of features, should be perfectly accurate, as close to perfection as possible. Which simply means your training model cannot afford to have any error. So peg your bias. We'll worry about variance later. Is this a universal model? Not at all. This is just an EKI recommendation if you're going to move to random forest. Step number 2, create a decision tree model. What do you mean by a depth of a decision tree? The depth of a decision tree is driven by the number of features. If I have one feature, there is one depth, 2 features, 2 depths, I'm doing overfitting, 3 features, 4 features, 5 features, I keep on overfitting, overfitting, overfitting. I finally try to reduce bias as much as possible. Does it solve my problem? It solves my one problem of eliminating or reducing bias. But then what am I left with? I'm left with a deep tree and tons of variance possibilities. Can I call it definitive variance? No. I'm opening my model with a possibility of a very high variance. At this point, have we solved all problems? No. Have we come to random forest? Again, no. Well, that is where step 2 ends. What is it that I've created now? I've created a deep decision tree. I have eliminated or significantly reduced the bias. But because my decision tree depends on a lot of features, because it takes this sort of target output to a higher end polynomial, because I've gone for extreme overfitting, I end up with a high variance. Now I need to reduce that variance. It takes you to that simple English phrase, having the cake and eating it too. In the context of pastries, that's not possible. But in the context of machine learning, let us try to find out how having the cake and eating it too is made possible. Now we come to random forest. Let us try to understand what is random here and what is forest here. You have a whole set of training data and you will assume that you will get only one output at a time. Rather than that, from that set of training data, take a random subset of data and create something called a bag. Then you replace them with another subset of data. You keep on creating bags and bags of data from this by taking, replacing, taking, replacing. This process is called bootstrap aggregation, or in simpler words, bagging, and that is step number 1 in creating the random forest. You would obviously understand that when I am creating multiple blocks and running the decision tree, I would get so many outputs, and taking the modal value of those outputs will significantly reduce my possibility of a variance. We have only come to one step of random forest. You would have noticed that when I used the choice of word clump of samples for looking at the subset of samples, why did I use the word clump? That is to give you a feeling of a clump of trees in the random forest context. Now, from bagging, we move to what else we can choose. Over and above choosing a set of data points, you can choose a set of features itself. Now, suppose I have 20 features or 25 features that is running my modeling and which is creating that large overfitting. Do I really require all these features, or do I really require a deep tree? I can carefully choose the features which I do not want and eliminate them on a run by run basis. That is, for each run of the random forest, I can choose only a select set of features. One technique by which I can choose these features is called the MR technique, or the minimum redundancy maximum relevance technique. I choose those features which give me maximum relevance in explaining the target and eliminate those features which are correlated to each other and hence create an intrinsic redundancy. One typical way for looking at the choice of the number of features would be, if you have 25 features, you go for the square root of that for one run, that is 5 features per run. This is not always standard. This is a recommended back of envelope technique. So by reducing the number of features, what I'm doing is pruning the tree. I'm still having all the advantages of a large tree. I'm still having all the advantage of multiple features. I've moved away from my linear model, but I've pruned the tree and created multiple prune trees. Each of them is a weak learner. The trees together become a stronger learner, and that technique is called tree pruning, step number 2. So by randomly choosing a set of data points and by randomly choosing a set of features, I create a random forest. The diagrams above which you see are clumps of random forests, and finally each of them will give a decision. I take the modal value of those decisions and arrive at a far more superior way of reducing my error. Just to complete the story, there is one more step, and that is called boosting, which can further reduce the error. If bagging was a parallel technique, boosting is a serial sequential technique. What does it do? It takes one output and tries to find out what are the weightages of the functions of that output, and whatever weightages are wrong, it artificially boosts those weightages, feeds it back, runs one more time, feeds it back, runs one more time. If you can do it iteratively several times, the possibility of my total error significantly comes down. Is there something called a zero error model? Is there something called zero risk in life? No. Risk never becomes zero. Similarly, in data modeling, error never becomes zero. It's all a question of how you can eventually reduce the total error, total bias error plus total variance error, using bagging, tree pruning and boosting, and creating a huge random forest. Before we close this video, let me take you through the decisions that you have to take as a data scientist, as a data analyst, before your machine starts taking decisions for you. Decision number one, do you want the so-called linear model, or do you want to go for non-linear modeling? Every time a non-linear model is not required. Decision number two, how many features do you require in your so-called non-prune model, or what is the level of polynomial definitions which you require? Decision number three, are you going to do for bagging? Then what is the ratio of your bag size to training model size? Decision number four, if you're going to do data pruning, how many features you need to take in the pruned tree vis-a-vis the total number of features, and what is the logic by which you would take that? I mentioned about MR/MR/TU. The next decision, are you going to do boosting? And then if you're going to do, how many iterations of boosting do you require? You keep on doing boosting, you lose precious resource time. Now, if you're going to move outside random forest, then what is the business model itself are you going to take? Is it a non-parametric model like a k nearest neighbor? If it is k nearest neighbor, what's the value of k? How many nearest neighbors are you going to choose? 2, 3, 4? What is the value of k? If you're going to do ensemble modeling, how many parallel ensemble models you require to arrive at the final modality for your classification? Your hyper parameterization tuning can keep going on and on and on, but I need to close this video at this point. I normally plan to keep my videos about 10 to 15 minutes, but my previous video in association went to about 20 minutes. People who saw it liked it, but then told, "Sir, it's slightly long." I have made no amendments in this video. This video is longer. Trying to make you understand what is classification, what is a trade-off, what is modeling, how to reduce bias and variance together, and how to conceptually build a random forest. It takes its time. I think it should have gone to about 25 minutes. Hope you like the video. A complete watching will give you a fairly good idea on classification modeling itself and building of a random forest from a very, very conceptual point of view. As usual, if you like it, press like. If you have not yet subscribed, subscribe to this channel and leave your comments. This is an interactive channel. Thank you, ladies and gentlemen.